Good morning, everyone. Thank you for joining us again for what will be the last in my current set of training delivery. And I'm very excited that today I'll be talking to you about forecasting. For anyone who saw Dan's comment, you'll notice I am not wearing a funky tie. I am not Michael Fish. We're not going to be talking about weather forecasts. For many reasons, they're very complicated. But what we will be talking about is forecasting with the perspective of health services. So hopefully very relevant to a lot of people. And the day will be split in two. First of all, we'll be doing some theory this morning just to help you understand, well, what's involved and what makes up time series data, which is often what we're looking to forecast into the future. And then actually thinking about ways that we could just look for very simple methods to see, well, can we get a prediction just using a historic value, so something like an average, and there's some more complicated ones, and often you'll find that it may be just as good to use one of those as one of the more complex methods, which will take a lot more time and data cleaning and data preparation and all that jazz. Part of this course is to help you consider what you'll be using it for and how important the accuracy is. And obviously, we'll be talking about how to assess the accuracy too. Great. So let's get going. So, as I say, what we'll be covering this morning, what is a forecast? Sounds simple enough, but there may be a few surprises in here for some of you. Next, we'll be looking at the process of forecasting itself. So if you were to do a forecasting project, what would the steps involved entail? And remember that maybe forecasting may be one part of a much bigger project. So there's plenty of scope there. We'll be looking at time series data in health. Calls to ambulance calls, so on and so forth. And then, as I just mentioned on the prior slide, we're talking about the importance of benchmarking. And these are these really simple approaches that you can try before you go on to do some of the big, fancy, complex stuff. So today, or in this course, we'll be covering Profit, which is a forecasting model from Facebook. There are others available. So you've got ARIMA, and then you could also use an ensemble of neural networks, which are outside of the scope of this. But if anyone's interested, let me know, and I will give you some resources. But as I say, it's really important to try these benchmark or naive forecasts first, because actually they may be no better than something that's a bit more whiz bang. And then the final thing that we'll talk about, obviously, is evaluating forecasts. It's very, very, very important. If you're ever going to be doing this in the real world, no matter what you come up with, you do need to evaluate it and make sure the stakeholders who are using your forecast are fully aware of kind of how good it is, what the potential pitfalls are, if there's any glaring issues around certain events. But more on that later. And one of the good things, just as a sneak peek, Facebook's Profits, which we will use in this course, is actually very, very good at working with what's called spiky events. So if you have a particular thing that may say Christmas Day, call volumes drop, or New Year's Day, they go up, these once-off events that occur regularly, as in annually, it is very good at predicting those, which is a little bit different to some of the models that are out there. So just to put it out there right at the get-go, I want no one under any illusions, but forecasting is difficult. If it wasn't, I think, there'd be a lot more people making money on the stock market and things like that. So you can come up with a forecast, but whether it's any good is where the difficulty lies. And obviously, a lot of that is due to the uncertainty of the future. I'll mention it once now, and I'm sure I'll mention it again. Who would have thought, sitting in January 2020, where would be 3.5 months later, and what that event, obviously COVID, had on forecasts for lots and lots of different things, hospital appointments, everything, everything from restaurant bookings to holidays and so on and so forth. And so some of these events you just can't plan for, you cannot predict. And that's what, the future can hold. And the other thing to be aware of is that the general approach and the tools are very actually statistically complicated. But the great thing is, especially with the likes of Profit, they've taken all the hard work out for you. So a lot of the wizardry that is done is kind of done under the hood, and it's done automatically. But they do still give you a few knobs and dials to kind of adjust and tweak things. And so it makes it much more available and easy to use for more people, which therefore increases the amount of forecasting that can be done. So there is some good news in this. So if anyone was to be embarking on a forecasting project, the main stages are listed here, and we'll go through them now. So really, you'd start with the problem definition. So really, what are you trying to forecast? But kind of more importantly, how will it be used? And we'll touch on why that is so important shortly. There will then be your data collection. And this is, again, very, very important because when you think about what you're trying to forecast, if you're trying to forecast hourly call volumes in a call center to make sure you've got the right staff, but historically you've only got daily totals of calls for whatever reason, you're probably not going to be able to do it. So you just need to be mindful what you're trying to do in the future is the evidence or data to support it from the past. And then you'll also need to be aware that sometimes you may need to pre-process the data to get it into a usable format so it can be used for the forecasting process. You'll then have your exploratory analysis, and that is more than likely going to include visualizations. So again, a lot of data science projects, you are going to do exploratory data analysis just to understand what you've got. If there's any major problems in it, as I say, March 2020, things maybe go and drops. Well, that's going to be a bit of a problem for forecasting the future. Obviously, as time is moving on, we're building up a history of the new normal. But again, something to be mindful of maybe in another event that impacts the particular data set that you'll be working with. Then this is the next stage is kind of the real chunky and meaty parts. This is where you'll be trialing and fitting different candidate forecast models. So obviously, as I said, likes of Profit, potentially if you're getting really into this arena, or if you want to go hardcore, the neural networks. And again, like anything, like we're trying different machine learning models, you want to assess the performance of different ones to see which one offers the best solution. And then finally, you're going to generate the forecast. And actually, well, what does the forecast actually look like into the future? Does it look reasonable? Does it look good? And it's really important to kind of get some engagement maybe with stakeholders who know the subject matter and know historical events that that kind of feels right. They may be able to tell you a very good reason why something, for whatever reason, doesn't smell or look good. So next, we have to think about what is actually forecastable. There's no point trying to come up with something that it's not possible. So the types of things that we can look at will be, as I mentioned an example earlier, call volumes in a call center, and that may be used to help to determine staffing levels. So that's not a tangible asset that you're forecasting. But then on the other hand, well, you may want to look at inventory management. So, within hospitals, what are the rates of the consumables that are getting used? Even for, departments like pharmacy, I say that with my background, being able to forecast, well, kind of what stock levels they'll need of particular items, that can be quite powerful to make sure you've got them in stock and then they're always available when they're needed. You may want to forecast outpatient appointments because that may help with clinic design, as in, where we physically locate the clinic, how many rooms are available, how many specialists, doctors, nurses, or whoever needs to be involved in that clinic are going to be available to make sure that you can handle the throughput of patients that are anticipated. Elective operation demand, again, quite an important one and pretty topical at the moment. And then you've also got something like the spread of disease, which is exceptionally complicated and definitely outside the scope of what we'll be talking about here today. But again, just to be mindful that it is something you may want to forecast. But there's other elements that we may come into it, as we touched on with Dan, with the agent-based simulations. And then kind of the step beyond that is then to consider, what are the forecast horizons? So the forecast horizon is basically, how far into the future do you want to look? In what units will you be looking at? So, for example, particularly with, I think in examples of industry, sometimes you only need to go minutes ahead if you're looking at machinery use, but you could all be wanting to see the forecast in hours, in maybe weeks, months, or potentially even years. So it is important to think about what you're using, where it's come from, and how it's going to be used, and the granularity that it's going to be required in. So there's some things, obviously, it can be easier to forecast than others. And how accurately we can forecast something, it really is determined by a number of different factors. And these include how well we understand the factors that contribute to it. So is weather going to be important? If you were forecasting, say, road traffic accidents, weather obviously does have a big part to play. There is added complexity of that, because then you need to forecast the weather if you want to forecast the other thing. And so there's more variables that need to be considered. You've then got to look at, well, how much data is actually available? And some particular methods are very, very data hungry. They may want to look at intra-hourly data points, intra-daily, weekly, monthly, so on and so forth, depending on what you're trying to do. They may need lots and lots of data. As I said before, if you want to forecast hourly calls in a call center, but you've only got daily level data, that's going to become a bit of a problem. And there may be situations where you don't particularly have enough data, and that's fine, but it just means you're going to have to use a less sophisticated model, and that's okay, but just to make sure you understand the kind of the drawbacks of that as well. And then obviously, if there's any changes in practice, we need to be able to consider how they are going to impact the forecast. And it's also good to remember that if you change a particular practice, you don't know what it would have been, as a result of modification, X, Y, Z happened, but how do you know what it would have been if you hadn't changed that practice? So sometimes there's a lot going on, and you can't always control or estimate them. And then, the example we give here is, what would have happened if the NHS as a whole didn't amend their practice when COVID hit? Well, we presume it would have fallen over, but we can't actually prove that, because things did change. We did stream patients and so on and so forth. And so it's these things that you just need to really, really be aware of. So when it comes time to actually do your forecasting project, and you've got to work with the stakeholders, there's some really important questions that you need to ask and really get them to consider as well before embarking on something like this. So one of the most important ones right at the top is, well, what decisions is this forecasting model going to help to support? Because obviously the importance can vary greatly. So if it's a short-term operational decision, so how many staff to have on a particular shift, obviously that's important. But if it didn't go well, you could rectify things and get more staff on the following shift, so on and so forth. So one of those things is the short-term operational decisions. But then if you're getting into something like determining future resource requirements, you need to be quite certain, and it's probably also worth adding disclaimers around any forecast that you're providing to those stakeholders to make sure they're aware of any limitations with it, and to make sure that they build elasticity into their plans. And that really goes on for strategic planning or resource planning over the long term. Imagine if someone was going to build a new facility based on the forecasting data you gave them. You'd hate to get it wrong, because that could be a very costly mistake, either with a facility that's too big, a bit of a white elephant, or one that's too small and just simply cannot handle the capacity, and then needs to go further modification very soon after it's opened. Then we'll need to consider, well, what do you actually need to forecast? Is it just
one
thing, one number, or is it going to be multiple things as well? For example, you may want to see how many people do we think will attend ED, emergency departments, or do we want to break it down and do we want to start looking at demand per condition, per age group, and then with that, just really consider, what is the actual need of the organization? Just because they may say they want it, what do they actually need and what are they using it for, to make sure you can kind of reach that happy equilibrium. Again, how accurate does it need to be? Would the average of the historical data actually suffice? And again, we'll look at how sometimes that can be more beneficial. Then we'll be looking at how far ahead do we want our forecast to run? So what is the horizon going to be? And then also, what is the frequency of the data? I've already touched on it a couple of times now. And, if it isn't in daily level, you may need to process it to get there. But again, you're kind of working on the rule of averages there. And then quite obviously, we can't provide daily forecasts if only monthly data is available. That would just be silly. Dividing the monthly number by the total of days in the month, it's all going to be homogenous. That's probably not that useful to anyone. Then the other thing to consider is how frequently are these forecasts going to be needed? Are you going to do it every day for the following day, every week, so on and so forth? So again, these are all the things you need to make sure that the stakeholders have thought of and thought through, and that they're aware of potential limitations to make sure that you're going to deliver something that is beneficial to them, that is worth the efforts that could go into it, and is going to be useful enough to actually deliver on the requirements. So, big piece of advice, really have to emphasize this. Make sure you spend time talking to the people who are going to be using your forecasts, to make sure that kind of you understand what they're going to be using it for, what they have available, and then also, in the long run, could save you a lot of time, because what they may need is very superficial, but your interpretation may be incorrect, and then you go on and spend loads of time, you run all these different models, you do all the comparative analysis, when in actual fact, it's overkill. It's just simply not required. And probably they won't thank you for all the additional work, because if they would have gone with an average, it's not going to do anyone any favors, as I say. So with time series forecasting, which we'll be looking at, obviously it's quantitative forecasting, quantitative being numerical. And so the types of examples that we can consider are the monthly number of patients that are carried by ambulance to emergency departments. We could look at the daily number of patients admitted to a hospital with respiratory diseases. Or we could do something else, something completely different, and look at quarterly sales of toilet rolls in the UK. Now, as you can imagine, that third point is probably, I'm sure it's important to the salespeople for their bonuses, but ultimately getting that wrong probably isn't going to cause a bottleneck in care for respiratory patients who need to, potentially need urgent care in emergency departments. And the one thing with quantitative forecasting, it is always kind of running on the assumption that historical patterns are going to continue into the future, and that's the whole point of it. Obviously, the example I've already touched on, extreme events can break this assumption. And as I mentioned, what happened in March 2020 will probably be causing issues for some time to come. Think ahead about 3 years, and then after that we can start looking at patterns again. So hopefully we're coming out of it now, but still a lot of services within the health system are disrupted and still kind of reconfiguring themselves back to either a new normal or the way they were. So a lot of theory so far. Next, we'll get on to what everyone was probably expecting to see today, and that would be a time series graph. And for our first example, we have this graph here, shows us our weekly outpatient appointments. And as you can see, we've plotted this chart over time. So it starts, 2014 and goes to some point in 2018. We can see that we've got, regular dips just before the end of the year. So as you can see in 2015, 2016, 2017, 2018, maybe that's Christmas Day. We can see there's a bit of a cyclical pattern. So numbers tend to be, excluding 2017 onwards, you'd say things are higher around the winter months, and then it dips, so a bit of a U shape. And so what we need to start doing is, or what the algorithms will do, is start looking for different properties that may not be visually identifiable within when looking at the data like this. And these properties are like signals for it, helping it to kind of determine where it's going to shape its future forecasts. So looking at these ambulance dispatch data, looking at the frequency, we have daily level data available, which is fantastic. And as you can see, it's quite noisy. It's quite difficult to pick out really what's going on. Obviously, we can see our spikes in demand. Again, let's assume that's the end of the year, or New Year's Eve, New Year's Day. You can see always quite big. And overall, there's a trend looks relatively constant, but you do have some cyclical patterns within it. But then if we start looking at that and looking at total weekly numbers, it kind of increases the resolution a little bit. And then it's easier to start identifying some patterns that are going on within the data. And again, to kind of adjust our resolution again, looking at the monthly level data, again, far easier to see the patterns. And actually you can start to see, there are cyclical patterns, but as we can easily tell with the yearly level data, obviously just watch out for the y-axis, there is an upward overall trend. So again, comparing that to the daily level, it didn't necessarily, it wasn't so easy to identify the upward trend over the different years. So there are different statistical characteristics of time series data, and these are the trends. So as we saw in the yearly data, overall, it just tends to be moving upward. We've got our seasonality, and that is within, let's say, for example, an annual period. Does the time series kind of rise and fall periodically? So, up and down. So we could say, winter may be busier, summer's quieter, and it just follows this kind of cyclical pattern. We've then got our mean or our average number, and this is also referred to as level within the literature. We've got our variance, so the peaks and troughs, how much does it vary within that? But then there's two things that you may not have heard of or considered before. We have something called stationarity, and there's a few different definitions of this, but the one I found that I like, stationarity overall, if you look, you're looking at overall data and you want the mean or the level and the standard deviation to be constant, so it's not heading up or down, and you really don't want any seasonality in it, relatively constant data, so that would be referred to stationarity. And let's say you had 3 years worth of data, it would mean that you could chunk up the 3 years, and then year 1 would look similar to year 2 as would year 3, and that's a good way to think of it. You've then got something called autocorrelation, and this is where the numbers within the time series are related or correlated to another factor within it. And an example here may be, let's say you may start to uncover that the number of sales on a Thursday actually have some kind of relationship to sales on a Wednesday. It could always be 10% higher for whatever reason. And those sales on a Wednesday could actually be related to sales on a Tuesday. So there's kind of relationships within the data that kind of have them connected to one another. And so next, we're going to be talking about these naive benchmarks, of which there's a couple of different available. So obviously, they don't kind of require large amounts of processing power. They're just a bit more simplistic, but in some respects, they may actually be better than what you can spit out with using something more complicated. So the first one we're going to talk about is something called seasonal naive. And so we've got, you can see the blue line was the training data. So this is the actual, this is what we know. And we can see overall, it has a positive upward trajectory, upward trend, which is great. We've got data obviously running from 2014 to the end of 2020. But then we run into our forecasts. And so our red line is our point forecast. And this is a single number that the model will spit out to say, well, this is what I think it will be. However, because we're using often statistics, or the model is using statistics to do this, there's a kind of a distribution, if you like. So the red would be the peak of the distribution. But then we have different prediction intervals, so these PIs. And so as I say, the forecast prediction, or the distribution will look like this. So if we wanted to cover 80% of the prediction interval, that would be the yellow bar. So that kind of gives you a bigger leeway. And then to give the 95% prediction interval, that is the additional 15% covered by the purple. So you can see that with the seasonal naive, it's followed a bit of a pattern. And if you look, the last 12 months, you will see for these 2 years that are forecasting, the line is exactly the same as this one. So it's just taken the last period, kind of shifted it to the right, and then it's done the same. And then obviously over time, the prediction interval will grow because certainty will reduce as we move into the future. So with these naive benchmarks, as I've mentioned already, you should really use these before you start looking at anything more sophisticated, because ultimately a clever model may not be as good as you think it is. And in some situations, it may actually even be worse than naive model. But unfortunately, the burden of proving the superiority or not of any model will rely on you as the people who are actually coming up with it. I've just seen a question about the prediction interval. If it's all right, I think there's another slide that will cover it a little bit better coming up, so don't worry, I'll come back to it. And so the classic naive models that are available are as follows. So we have what's called naive 1, and that's simply just you've got your actual data, and it will just get the last actual point and carry that forward as it is, and that will be the prediction. We will have our seasonal naive, and then that kind of, as we saw in the chart on the last screen, it kind of follows the last period, and it will just kind of replicate. It'll just do that over and over again. We've then got something called drift, which is basically naive 1, but instead of it being a flat straight line, it will kind of follow a simple trend or simple trajectory up or down. And then we've just got the average. So it'll look at all of the data there, and it will just go, what is the average moving forward? So a little bit different to naive 1. And the models produce point forecasts, and as I say, the prediction intervals. So it's basically talking about confidence intervals, thinking about the certainty with which you're making the prediction. So I'm going to forecast tomorrow that I don't know, the Spar shop down the road from me is going to sell 70 1-litre bottles of milk. And I'm doing that based on all of this data, but that is with, kind of what's my confidence around that? I'm just trying to think if this is a good way to explain it. The chances of it being bang on 70 are pretty slim, but it could be 75, it could be 65. And so you want to give it's kind of like the leeway with which you've got the certainty that the prediction will occur. But I think, again, with the code alongs, it probably explains it a little bit better. And so next, we're going to be looking at evaluating the forecasts. And so if we're thinking about the point forecast error, so this is kind of like, as I say, when I say the 70 litres of milk I'm going to sell, this is like the middle of the distribution where I've got, the middle of the road for the guesstimates that I'm going to come up with. Again, we can see here, we have our actual data, and so the blue line, following that there. Then with our, we will then start to look at, so the point forecast is the red line, but the black dots are like our test data. So imagine we held out some data. Well, we can see initially, yeah, all right, the red line's close to the actual, yeah, close. Then we can see it's starting to increase, get further away. And then once we get past October, we can see that actually the prediction, which is the red line, is quite far away from the test data. So as I say, we've got on the left the training, the right the test set, and the difference between the ground truth and the predicted value, is good to a point, but then it kind of tails off. And at this point, it's not even within the 95% confidence interval, prediction interval. So not ideal. And so there's different ways that we can measure the point forecast accuracy. So one of those is just looking at the mean errors. And this suffers from some errors being positive and some being negative, so not perfect. But then if we wanted to kind of have those that are better scaled, we've got our mean absolute error and our mean squared error, which again is related to our root mean squared error. We've then got relative measures, so the mean absolute percentage error MAPE, or the SMAPE, which is the synthetic mean absolute percentage error. And so the percentage errors I think we'll be looking at in the code along, they're good because, as I say, it's relative. You can say, oh, it's within 10%, which probably means a bit more than it's within 50 units, depending on what you're using. And then we've also got, finally, the scaled errors, so mean absolute scaled errors. And the great thing is that the methods we're using will spit out all of these values, and then you just choose from a dictionary which one that you want to pick up. And then just with the prediction interval coverage here, we can see, as I mentioned earlier, from January to kind of September, that actually the prediction interval, the forecast, the red line, was pretty close to the actual test data, and they're sitting within the 80% prediction interval, so they're quite close. They're good. However, from October onwards, the prediction was much lower than the actual or the test data, and it sits outside of the 95% prediction interval. So again, not ideal that the prediction is so far off the mark. How useful would that be, given it's so badly underestimated things? Imagine if you'd planned staffing capacity based on that, you potentially could be overwhelmed. So not ideal. Okay, then. So there's quite a bit of me talking. What I would propose we do now, if we're okay, we will have a 15-minute break. We'll come back at 10:17, and then we'll start working through the code alongs, if that is okay with everyone. So I will see everyone back at 10:17. Cheers. Hello again, everyone. So just quickly, I'm just thinking, before we move on to the code along, I just wanted to talk a little bit more about prediction intervals. I appreciate that people haven't got a background in statistics, or they haven't looked at studies that cover things like confidence intervals. It may be a little bit of a new concept. So I've got an example that I've just come up with. And just hopefully it will illustrate things a little bit better. But if it doesn't, let me know afterwards and I can circle back. But let's say we have a Duracell, or other batteries are available, brand of battery manufacturer. And they tell us that this battery is going to last for 105 hours. I know there's a lot of variables, temperature and what it's going to be used in. But let's say they tell us 105 hours. Let's say it lasted for 102 hours. Well, technically, it's wrong. We were told 105, but it lasted for 102. So you'd say wrong. But with a confidence interval, they could tell us, well, we think it will last for 105 hours, and we have kind of a 95% confidence interval around that. So that could mean it will last for between, on 95% of occasions that these batteries, this and all of the other ones at the factory, will last between 100 hours or minutes, whatever, 110. So on 95% of occasions, it's going to fall somewhere within that limit. And it's kind of like the tolerance. And so now they've said to me, oh, it's 105 and that's 95% confidence, or 100 to 110. Okay, yeah, I know that I can buy it reassured that on 95% of occasions, it will last between 100 and 110 minutes. Similarly, with a forecast, if you say, oh, I forecast that, about 70 litres of milk are going to be sold that day. Well, if it was 69 or 71, it will technically be wrong. So I start to give it a kind of a tolerance, a prediction interval. And I can say, well, I'm 95% certain that you will sell between 65 and 75 litres. And so if I get one of those values, well, that's fine. But if it was outside of that, then you go, oh, well, it wasn't within that particular interval. And so that kind of gives the worth of the prediction in the first place. And so the practical reasons for that, again, if you're planning call center staffing and you say, well, I'm expecting 200 calls in that period, but that's, plus or minus, then it gives people, it gives the management opportunity to say, well, actually, let's cater for the worst case and let's get more staff in, or we'll get the minimum number of staff in that we could stretch to that higher level of the tolerance. But obviously, if it's outside of that tolerance, that's just going to cause a bigger problem. And just to confirm, no, I'm not meant to be sharing a screen. It was just me. It was just me and my battery. So anyway, I hope that may go some way to explaining it. If not, let me know and I'll make sure I come up with something better for the afternoon. But on with the code along. So, sorry, I shall, sorry. Just having a moment trying to get the right screen to share. Right. So if you've either downloaded and used the local environment within the 9A Intro to Forecasting, there are 3 files in the code along. We're going to be working on the first 2 now before we work on before you're working your peer support groups on the first practical in the exercises folder. If you are using Binder Hub, the links are online, so hopefully they are all working as expected. Just checking, can everyone see Jupyter Notebook?
Yep.
Yep, fantastic. Thank you very much. So hopefully everyone has access to this either on the local machine or Binder Hub. But what we're going to do now, we are going to be loading some time series data, and we're going to use them, load them into pandas, my favorite. And then there's a couple of extra things that we're going to need to consider because we are dealing with time series data. So obviously pandas usually have an index, usually 0, 1, 2, 3, 4, like a unique identifier. But when we're working with time series data, we want that to become a date time index as well, so not just an integer. We also have to tell the data frame what is the frequency of this time series index. Is it daily, monthly, first, 2nd, 3rd of January, or is it the 1st of January, 1st of Feb, 1st of March, so on and so forth. We also need to consider the format that the dates are in. That can be everything from US versus UK format, so month, day, or day, month, year. But, there may be situations when you're just given a CSV and it's 2018, and so it only has day and month data in there. So you have to parse the dates accordingly to make sure that it's handled correctly. And as ever, I've tried to just put the references here for the documentation, should you need to read some more. But as very, very familiar now, let's import pandas. And so just a bit of a sneak peek what we're doing. A non-health example, probably couldn't be further from health if we tried. We've got this alcohol sales data set. So the great thing is we've got data here from around 1992 through to 2019. So lots of data within. And it's quite an interesting one for a number of reasons. We can see Within each year, there appears, if we look at each year in isolation, there appears to be seasonality, kind of a cyclical variation. There is obviously an overall trend heading upwards. And then there's also the variability. So the kind of the difference between the peak and the trough, the highest and the lowest. As you go on, that tends to grow. And so this is actually called multiplicative seasonality. Sorry about that. I'm just going to make this a little bit bigger. Hopefully everyone can read that okay. So as you can see, the peaks and troughs down here are a lot less than when they get towards this later stage. So the first step is to read in the CSV. So we're just using standard pandas and standard read CSV functionality, but there's a couple of extra things that we're going to consider. We've got parse dates. That is a variable, an arguments that you can configure. And we're going to set that to true because we're going to tell it, yes, there is data available within that. We are also then going to say, well, what column are we going to set as the index column? And in this particular data, in fact, I'll open it just so you can see how it looks. In fact, it's going to be easier to do it this way. Alcohol sales. So we can see here two columns in the CSV. First one is the date in year, month, day format, and then the total number of units sold. And then an optional argument, because it's UK data, it's going to have date first. So there's this parameter here, date first equals true. And then after we've done that, we then need to consider the offset alias. So is it daily frequency, monthly frequency, which is MS, as in month start, 1st of Jan, 1st of Feb, 1st of March, which is, as we can see, this is what we have, 1st of Jan right through to 1st of December. So it is monthly start data. But let's just get the data in. You'll notice here, I'm just creating this variable called URL. Still breaks PEP8 compliance, so forgive me. But essentially, it is just a link to the file online, and I did this for using Binder Hub. Then I'm creating a variable called TS, so time series. Pandas read CSV for this URL, or it can pick it up from your data folder. Parse dates equals true, and index column is date, all uppercase. So we'll get that loaded. And then, as we always normally do with pandas, we will have a look at the head. So we can see our index has been set as the date, and we know that because it's kind of offsets and in bolded. So that's the index. And then the sales or the values are in this column here. If we wanted to find out some additional information about this new time series data frame, we can use the .info method. And we can see there are 336 entries ranging from 1st of Jan, 1992, through to the 1st of December 2019. And they have 336 non-null values. That's great. So let's have a look at the index. And so we can see that the date time index, well, in this situation, these are the month start. So start, 1st of Jan, 1st of Feb, so on and so forth. But there are different granularities, if you like, available. And so you can get it right down to the nanosecond level. If you're doing, you need very laser focused predictions or horizons into the future. Obviously not the case here. And what we can see at the moment, it's currently set as date time 64, so it can get down to the granularity of nanosecond. But the reality is it's month start data, so let's set it accordingly. So we're now just going to say the variable time series dot index dot frequency, or frec, is equal to month start. And so when we run this dot index again, we can now see the frequency, as it was none up here, and it's now been changed to month start. And now that we've done that, we can see that the frequency is now reported here where it wasn't previously. So again, always important to make sure that you do set the correct frequency of the data. And then all of these stages, everything we've kind of explored above is just done in a few lines of code here. And that's just got everything consolidated. And then just to look at it again, there is it all ready to go. So hopefully you can see nothing too scary there, quite easy to read in using functionality, some of the functionality you've already seen, and obviously the familiarity with Pandas data frames. So then if we move on to the second code along workbook, I should say that all the code is provided in the code along workbook. So it doesn't matter if you haven't got two screens, you can focus on this. Absolutely everything is in the files you have. You don't need to add or append anything. And so the next part is really going to be exploring the data, and how we're going to do that. We'll do that by plotting what we have available. So what we're going to walk through in this particular notebook will be plotting the time series. We'll be adjusting the monthly time series to account for different days, different number of days in the month. So February 28, 29 versus July 31, because this can add additional noise. We're then going to run what's called a smoother over the series to see if that can help us identify a trend. And then we're going to break the time series into trend and seasonal components using something called seasonal decomposition. Don't worry about that too much, just seeing is believing. And again, we've got the references to matplotlib, pandas plot, and then the function called rolling, which allows you to kind of get a rolling average or mean or median over a certain window. So it'll look at 7 values and say, what's the average over those 7? It's this. Then the 2 through 8, so on and so forth. So you get the rolling average, kind of, because it's a way of smoothing. But the imports that we're going to need here are pandas and numpy. We'll also include matplotlib, so we'll pyplot dates style. And then for this seasonal decomposition, we've got an additional library, which we probably haven't seen before, and this from statsmodel.tsa.seasonal, import seasonal decompose. And then just for these workshops, we need to make sure that we're using, or we should be using, version 0.11.1. It's not critical, but it is highly recommended. So again, maybe something to think about if you're doing a project on this and you're referring back to these assets. Try and use the same environments, just because you'll know the expected functionality. So next, we're going to have a look at this ED arrivals data set. So this is adult arrivals into the emergency departments between April 2019 and May 2020. And again, just remember, if you need to see a full list of the different frequencies that are, or the offset aliases, you can click there. That will take you to the documentation. So whole load to look through. And the data itself, I shall just open here. So again, 2 columns, date, so year, month, day, and then the number. And so again, this is stored on the cloud, but we're going to store that as URL. We're going to read in the CSV from that address. We are going to create the index column on the date column, and we are going to parse dates, and we're going to set the frequency as month start. And it would help if I actually imported the libraries first. So just having a look at the shape of that, as we already saw, there are 2 columns, which then when you set the frequency, reduce that down to 1, so 98 observations. Let's find the earliest date, and we can do that with the .min function. We can see here the 1st of April 2009. And that runs through till the 1st of May 2017. Sorry, I showed you the incorrect data. That's why I was looking a bit. This is the ED monthly start time series. So again, 1st of the month, January, so 1st of April, May, June, so on and so forth. That looks a little bit better. And you can see here it's added in the frequency when it's looking at the timestamps as well. And so next, we are going to use matplotlib to kind of visualize the time series. And we'll do this by, we've got our variable, the ED month, and we're just going to simply use .plot. And then we're going to specify the figure size. So again, if you remember, if you're within the parentheses and you're in something like Jupyter Notebooks, Shift and Tab will bring up the doc string for it, or the help information. So clicking on the plus allows you to read more about the different arguments you could want to use. So we're just going to specify here the fig size of 12 by 4, meaning 12 wide by 4 high. And then very quickly, we can see we have got our time series plot. You can see the y-axis isn't centered at 0. But overall, we can start to see we've got, looks like some seasonality. We've got an upwards overall trend. So, you know, it looks like quite interesting data. But it's also important, it's good to remember that once you've plotted it, you may want to save it or export the figure. And you can also do this using the, we assign it, the figure itself, think of it as a canvas, using the .figure method and save fig, and then we're just going here, we want to save the outputs to a PNG file. So that could be useful if you wanted to put it into word processing documents to share with stakeholders. But next, let's see, you know, that's a pretty plain plot. If we wanted to start adding a few more elements to it to make it easy to understand, here's just some of the arguments that we can use here. So obviously we've still got the fig size, it remains the same, but we can change the color that we want the line to be. We can have a play with the different line styles. We can have a look at the markers. We want triangles, and then also the line width. So if I run that, you can see it looks quite visually different. Let's say I want to play around with the marker. I'm changing the hat for an asterisk. And again, it's moved it to a star. Let's say I wanted this to be red. You can just have a play with all of the different values available. Change the line width, obviously whatever floats your boat. And there is a link to the documentation here. So you can have I'll let you kind of dive into that, so you can see what all the different arguments available are. And so let's say, great, we've improved the visibility a little bit, but if we want to start adding some labels, we notice we've already got the date because we set that as our index. But let's say we wanted to add the y-axis label. We can do that by setting the y label here. And let's say we also wanted to change the, at the moment, you know, the y-axis only runs from, you know, just below 8,000 to just above 11,000. We can specify in this y-lim argument here, method, sorry. And just in case you've never seen it before, you know, when we're writing numbers in plain English, like it was 6,000 would be 6,000. Well, you can use an underscore here to improve readability. So 6,000 would be 6_000, 6 million, 6_000_000. And it's just acting as a comma, just again to help the readability of the code. And you can see here now, we have got our y-axis label has been added here. And then we also have, we've pushed out the kind of the boundaries that we want to run for that y-axis, running at 6,000 through to 12,000. Again, you can have a play with those. And so obviously we've been using matplotlib. There's something called Seaborn, and this package actually allows us to improve the quality or the impact of the graph. And if we want to do that, if we want to take advantage of this, we just input Seaborn and the standard alias is SNS. And then we're going to set that. So we'll run that. And then we're going to see how using Seaborn has now improved the appearance. And we're just assigning it to a dummy variable here. And so it doesn't look too different here. However, as we move on, you'll start to see that the visualization gives a bit more detail. And so what we want to do now is adjust the values for the number of days in each month, because as you remember, we're reporting monthly level data. And let's say a month that, like February has 28 days in it versus July has 31. Obviously, if you saw a smaller volume, let's say there was 100 a day, it would be 2,800 versus 3,100. Even though actually the daily level rates will be the same, what we're going to do is just see how many days are in each month. So you calling from the index the days in month, and that's automatically told us for the index that we've used for this particular data, the 30, 31 or 28 days. And so what we want to do now is find out, well, what is the daily rate? So the monthly values divided by the number of days in each month. And so we're going to create this new variable called arrival rate. We're going to look at this arrivals column, and we're going to divide it by each of these numbers. So the respective number will be the denominator. And once that's done, we can have a look at this new variable we've created, and we can see it's still picked up that it's time series data. It's got our month start frequency, but we now know that the daily rate, so in the month of April 2009, on average, we were seeing 298.26 cases, so on and so forth. Just comparing that with the monthly level data. So you can see, obviously, that would be 30 days times that will get to this value. And so if we now want to compare the two, so looking at the monthly level data versus the daily rate, we're just going to call the figure, so that we've already seen this one. But then when we have a look at the daily rate, we can actually see, I'm just going to have to zoom out a tiny bit just to show you. It's overall, it's smoother. The data it's a little bit smoother and easier to identify overall trends and what exactly is going on. So there are obviously benefits to this. So next, we're going to run a what we call a smoother over the time series. And this is often because the time series are subject to seasonal patterns and noise. And this helps us to kind of explore things using a moving average. Now, I mentioned the rolling function method before, and this is great for creating this rolling average. And so if we want to run a 12-month moving average over the data, we would create a new variable, MA12, and this is the arrival rate, which we've already calculated, dot rolling, and then we want the window of 12. And then if we wanted to have a plot of that, we can now see, in addition to the original data, we've got this rolling, which is much, much smoother. The smoothed observations, which are being added on, which is the MA12. As you can see, it doesn't start until after the first 12 months because it looks at the first 12 months to then calculate the first value, and then it kind of runs on from there. It's a much smoother line, so easier to identify. Yes, there definitely is a positive overall trend. In the chat window, can I just ask what people think? How do they think this red line will look if we start looking at the 6-month rolling instead of 12 months? Do you think it'll be smoother or less smooth? Correct. And as you can see here, there's quite a bit more volatility because it's now only looking at the previous 6 values before it then starts to work out the average. And you can see here, it only waits till month 7 instead of waiting till month 13. So the final thing to mention for this part of the code along is to look at the seasonal decomposition. And really, a time series can be broken up to different components. So to help us understand the trends and seasonality that is present within the time series, we use what is called seasonal decomposition. And this is a model-based approach that breaks a time series into 3 different components. And this basic approach has 2 main forms. So additive and multiplicative. It was easier to say when I didn't have people looking me online. So let's consider the additive model first of all. So if we assume, and I apologize, I have a phobia of these maths terminologies, but I promise you it's quite easy to get your head around. If we assume that the observation at time t is yt, so that is the actual value. Thanks, Dan. And then we have the additive sum of the trends is t, the seasonality plus any residual error. So we know there is an upward, a slight upward trend. We know depending on the season within that 1 year period, we'll add that to the trend, and then any residual error. The final estimate will be the sum of each of those three components added together. And so something like this, you'll see, that between the upper and the lower blue lines, it's all kind of uniform. So it just kind of moves on into the future. So yeah, the width of the cycles and the amplitude will all be pretty similar. However, with the multiplicative decomposition, if you've got seasonal fluctuations that tend to grow over time, it's a really good model to use. And this is where you get our observation, yt. And this will then be the product, so the multiplication, and this is the maths symbol for multiplication, the dot. It's going to be the trend multiplied by the season, or the seasonality, multiplied by the random error. And so as you can see with this multiplicative seasonality on the right, that the spread kind of grows over time. And so it's handy to know, what's going on to decide which is going to be the best type of forecast model to use. But the great thing is we can look at our data and we can use this seasonal decompose and see what's going on and kind of plot it. So we are just creating a new variable, decomp, using the seasonal decompose function, passing in our arrival date, and we're saying here that we want to use the additive as opposed to multiplicative. So now we have our new variable. We can see the overall trend, so it's like it's applied the smoothing for us. We can see, oh yeah, there were between 2010 and 2013, there was a definite increase. Then the trend was kind of static before mid-2015 when it starts to rise again. So this is looking at the overall trend. Next, we want to look at the seasonality. And if we have a look at that one, we can see that when on average, that if we look at, let's say, beginning of the year, 1st of January of 2010, the estimates or the guesses that a future model will come out with will tend to be 20 less than this point here. I can't see exactly when that, let's call that November. Oh, sorry. Yeah, if November is at the 0 here. What this is saying is when we come up with a guess, when we're forecasting into the future, the values, the predictions it comes up with for this, New Year's Day will tend to be 20 less than the mean or the expected value. But similarly, later in the middle of the year, the months around here will have values that are higher. And that's kind of what contributes to the shape of the trend. And then finally, the final element is obviously our residual errors. And so we can see here that the residual errors will vary over time. And again, 0 at the end of the year, but you tend to get bigger areas and variances, middle of the years, essentially. And so what you do with this additive model is basically add all of those together to come up with your future prediction, which will be different to the multiplicative one. So hopefully that makes some sense. What I'll invite everyone to do now, in the exercise folder, we've got practical 1. So I will open our peer support groups together. Open the peer support groups up and allow everyone to go in, say hello to each other. And then using the 2 workbooks or the 2 code alongs we've already used, just to complete this practical. So all of the code is available for you in the code alongs, but you'll just have to work together. And I am going to give everyone, what time are we now? 50 minutes, if that's okay. So we will come back, or just over 50 minutes, I should say. So we will come back at 11:40, and then we will work on the final code along, and then there'll be a forecasting practical for everyone to try. So I'll open the rooms now. I'll run through, come say hello to everyone, and set any questions you have. But other than that, hopefully it's all pretty straightforward. Okie dokie, thank you. And see you back at 11:50. Sorry, 11:40. 11:40. Hi, everyone. Welcome back. Hopefully, there weren't too many issues there, and everyone was able to work through that relatively straightforward. I just realized that I wasn't 100% happy with the way I had explained the seasonal decomposition. So I just thought I'd talk you through an illustrated example using the data that you've just worked on. So we run the decomposition additive model here, and we can see we have, first of all, the overall trend line. And what I'm trying to illustrate here is how the model came up with, or how it's going to predict into the future, a final value, its prediction, based on the components that go into it. So bear with me while I step through this. If we look at this trend line here, we can see, and I'm just picking out January 2016 because it's bang in the middle, we can see the value here is around, let's call it 36.7. So there's our overall trend. Then if we have a look down, we notice within each annual period, there's the same repeating pattern. And again, January 2016, it's saying on average, there's around, let's say, 5 less than, the starting point. So that would break us down to 31.7. We then move down into our residual errors. Again, they're varying over time. There's no cyclical pattern there. We can see that in January in 2016, it's about a 0.9 reduction again. And so that would give us around 30.8 if we get the 36.7, which was the trend starting point, minus the 5, minus the 0.9. But if we scroll up and actually look at the actual data here, the actual training point or the observation was around 30.8. So hopefully you can now see how you get like the original starting point from that trend, and then the modifications you make to that to get to the final value. And that's kind of what the model will do in the future. That's what this decomposition is doing, is identifying the different elements that go into it. So hopefully that makes a little bit more sense. Okay, so if that is all right, I will just move on to the third and final of the code alongs. Apologies, my dog's just arrived home, very verbose. So with as I mentioned previously, before you go on and try and use any of the big and fancy kind of models out there, like Profit, for example, it's always good to use a naive forecast just to make sure that it's, that could be good enough for the purpose. So it's really worth going to any more effort. And so what we'll do in this is just have a look at 2 of the different naive forecasts available, Naive 1 and Seasonal Naive. And then we'll also be looking at prediction intervals for measuring forecast error as well. So with this, we've got our standard library imports. You'll see that on this row, we're actually going to use use ggplot, which emulates ggplot from R. And then we're also going to, ignore some particular warnings, just because we know in this instance they're not going to be valuable. Next, I'm going to create this user-defined function, this helper function called preds series. It passes in 2 arguments, data being a NumPy array, and the predictions. You pass in the data and as the data frame, and then the predictions as a series, and then it will spit that out for you. Now, just to point out, these 3 quote marks at the top, or apostrophes. You start and end, everything in there is in red. This is what's called docstring. I think it's been mentioned before, but it's just worth pointing out again. You'll remember I showed you that shift tab feature before, and that works obviously with libraries that you've imported. But because we've set, or this particular user-defined function has a docstring, if I do the shift and tab, just down in this cell here, by shift and tab, you then see that the text that appears is a carbon copy of what's written in the docstring above. And so that's why it's always a really good idea to put docstrings when you're creating your user-defined functions, because if someone else is using it or you've forgotten, you're able to quickly remember what are the inputs and what are the outputs for the particular function. Anyway, with this one, again, we're looking at the over 18s, or the adults emergency admissions. So again, just to show you the file here, and this one is daily level data. So the one I looked at by accident before, from 2017, 22nd of January. We're going to read that in a variable URL. We're going to create the ED daily data frame. For that data, we are going to pass the dates, and we're going to set the index column as the date column. And then we are going to set the frequency to D for daily level. So once we've imported that, we can see there's 344 observations ranging from the 22nd of Jan, which we saw when I looked at the CSV, through to the 31st of December 2017. And now let's visualize the data that we have. And just wanted to... So someone asked why we're creating the variable underscore. And just by creating the variable underscore, you can see we don't have this additional axis subplot that is hidden from us. All we get is the actual graph itself. Not mandatory, it is completely optional, just something to bear in mind. But as we can see here, it is quite noisy, lots of intra-month variation, up, down. They could be weekends, just at a quick glance. You can see the cyclical pattern over the course of the year. The trends looks pretty stable. So let's consider the different naive forecasts you can use. Now, some of my colleagues at Pencord have created a library called Forecast Tools, and here it is on PyPy. You can see Tom Monks, from whom these slides have been derived. But basically, this takes all of the hard work of doing the naive forecasts out for you. We've got the pip installation instructions there. But we're going to import that library. From that library, we're going to pull in naive one. Just something else that you should be aware of, similar to that shift tab, something else you can sometimes do is type in the word help, open the parentheses, and put the name of the module in. And in this case, naive one, and then it gives you a load of documentation for it. So this is giving the information, the help for the class. And so to use this, what we're going to do is instantiate this class. So we're going to instantiate naive1 as a variable called nf1. And then, similar to a lot of machine learning models, we are going to fit the daily data to it. And then we are going to get the prediction. And we're going to do that by predicting this fitted model. And we want to predict a horizon of 28 because we're working with days. This will be 28 days into the future. Then if we have a look at what are the predictions, you can see it's come back as an array, and there's 28 values of 184. And so why has it done that? Well, that's because the last value in the data frame from the actual test data, 31 December, was 184. So remember, naive one simply takes the last observation and carries it forward, because we're asking for a horizon of 28. It's just going to give us 28 to 184. So just so you understand where it's coming from. Then if we decided to plot this, we can see we've got all the code here. Our training data is the red line. Our naive one, when we have an observation, it tracks it, it follows it along. It's just shifted across by 1 day. But you can see when the observations end at the end of the year, it's just that value of 184. So it's just a continual straight line. That is naive one's prediction in the absence of any other training data. So just out of interest, what does everyone think about that? Do they think that is a good, bad, indifferent? If you want to put, yeah, I like that, terrible. But who knows? You know, it's always still worth assessing it just to see how it does compare. Forecast tools doesn't load. Is that on? Sorry, are you using that on Binder Hub on your local machine?
Local.
Okay. And do you just want to do a pip install forecast tools? I'll just put it into the chat window. Oh, sorry. If you put it into Jupyter Notebook, into a new cell, if you do an exclamation mark, pip install forecast-tools, hopefully that should install.
Fabulous.
I do apologize, everyone. I thought I'd tested that. Just making notes to update for next year. Okay, great. So I'm glad that's working. Again, if anyone else is having an issue, just remember exclamation mark pip space install space forecast-tools. I'll put that into the chat window when we work on the practical. So next, we're going to look at seasonal naive. And the good thing about seasonal naive is that it does introduce some seasonality into the naive into the kind of naive estimate that it's going to give us. So again, here, a new import line, and this one's called uppercase SN naive. And similar to before, we are going to instantiate a new object from this class. But we're telling it that we want the kind of the period of 7 days. And now we are going to fit our ED data to this object. And then we're going to predict a horizon of 28 days. So if we have a little look at what these predictions look like now, you can see the different numbers. So unlike naive one, which is 184, it does vary. If we're just looking at the last 7, we can see 175, 249, so on and so forth. But those 7 there, you'll notice that they just repeat once, repeat twice, repeats. So they just repeated 4 times to give a total of 28 observations. And then when we plot that, you can now see that, you know, all of a sudden, instead of just having that flat line at 184, it's working as expected. Or it is giving what seems to be much more indicative or reflective of the periods before it. So again, hopefully people will agree that this seems on face value, given that there doesn't tend to be an overall trend, this seems to be quite a good prediction. So next, we're going to talk about these prediction intervals that I mentioned earlier. So similar to the confidence intervals. And it's possible to get a model to spit out both the actual predictions, the point forecast, as well as the intervals, the ranges. And so to do that, we'll have our model, whatever model we've used, .predict, what the horizon is, and then we're just giving an additional parameter saying that we want it to return the prediction interval is true. And let's say that we wanted it to give additional prediction intervals. We can just change the parameters. And so you can see here, we're setting the alpha for 0.2, 0.1, and 0.95 to give us 80, 90, and 95% intervals. So how would that look in reality? Again, we would instantiate a new object with our period of 7, we'd fit our daily data. Now we are going to assign 2 variables simultaneously, y-preds and y-intervals. We'll see we've now adjusted our prediction, our .predict, so our horizon of 6 days. We're saying that we do want to turn on the prediction interval for true, and we're saying that we want it for 80 and 95%. So when we run that cell, the y-preds will get stored, but then the y-intervals is then a list of 2 arrays. So the first array will be 80%, and the second array will be 95%. And again, if I'm just calling the indexes of the list, you can see for each of the 6 estimates it's come up with, it's saying, well, you know, if I just put YPREDs, the prediction one is 175, and it's saying, well, with an 80% confidence interval or prediction interval, that's going to be, you know, I'm 80% certain it will range from 143 to 206 across that whole window. But if I wanted it to be 95% certain, it was going to go, well, it's going to be somewhere between 127 and 122. So it makes it much, much wider. So next, just a helper function. So again, feel free to copy and paste this. And this is just going to allow you to plot the prediction intervals that have just been obtained from the above. So once we've run that, we can then use this new function, and we're going to say, well, just first of all, I want you to put the training data, the last 60 days of the ED attendances, pop in the predictions, which will be the point forecast, so the actual numerical value it says, but then also put in the intervals as well, remembering that was a list of 2 arrays, one for the 80% and one for the 95. And as you can see here, the point forecasts are exactly the same as the last observations here. And then you can see the prediction intervals get wider depending on the 80 to 95%. So next, if you wanted to measure the point forecast error, just like with machine learning, you often you have a training and your test set. So you split up a small amount of data to then test the predictions against the actual, just so you can see how does it vary. Well, we do something very, very similar here. Again, we're just going to look at the shape of our data. So we've got 344 observations. And if we're saying, right, well, actually, I want to split the data and I want to have, I want to hold out the last 28 days because that's going to be what we're going to test the data on. I'm just going to get the training length. So that's going to be 344 minus 28. And then what we're doing, assigning 2 variables simultaneously, train and test. For the first variable, we're going to say, go from the value 0, the first value in that training data, up to 316, and then 317 through till 344. And then you can see the shapes here. So it's basically most of the data is training, and then the 28 days for the test. Then to compare that against the seasonal naive value, we are instantiating the seasonal naive again. Instead of doing 2 steps for fit and predict, we are now going to do it in a single function or single method. So snf.fit predict, passing in our training data, which remembers the 314 days with a horizon of 28. So this will then spit out predictions. Remembering we've already got that holdout, that test data, we kept that to the side. And so what we're going to do now from this forecast tools, we're going to import the forecast errors function. And then to get this working, we're then going to pass in the test data, remember the data we carved out just above, and we're also going to pass in the predictions as well. And so for each of the different, you know, the mean error, mean absolute error, root and squared error, so on and so forth, it gives you a load of errors. So you can see here that actually the seasonal naive, remember this is the one that kind of still gives you the shape. This is giving us a mean absolute percentage error of around 12%, which is interesting. Now, if we compare that against naive 1, remember that's the last one, just takes the last value, that 184, and pushes it off into infinity. It again comes predictions, again passing in the train data, so that was the 314 with a horizon of 28. It's going to spit out 221 28 times. And then when we run this forecast error again and actually done the test data against the prediction, you can see the mean absolute percentage error is actually less. So in fact, that one static number of 221 actually is marginally better overall than using something that looks a bit more intuitive. And so I just saw the question just about, is it possible to do this in R? I have to double check on forecast tools. Everything else is possible. And I know that profit, which we're dealing with this afternoon, is definitely available in R as well. So I'll report back on forecast tools. Sorry, I don't know off the top of my head. But anyway, hopefully this makes sense. Well, that's a really good question. So someone has just asked if there's an acceptable level for the mean average percentage error. And it depends on what you're using it for. If it's something a bit more mission critical, you'd probably have a lower tolerance of error, where if what you're using the prediction for or the forecast for isn't to it's not going to change the way you are going to long-term staff a facility, or how many beds a facility is going to have, then it's you're going to have a bigger margin for error. But it really is what's acceptable for the user. And again, you don't know. This is all testing, because you have got that test data able to carve out. You won't know about if your prediction's any good until the future, the time period that you're trying to forecast actually has passed. And obviously, if you're altering your behavior based on the forecast, you'll never know what it would have been if you hadn't changed your behavior. So it's a lot of I'm afraid how long is a piece of string, what is the purpose, what's acceptable to the stakeholder, so on and so forth. So I don't know there's a right answer to that, I'm afraid, or one single answer. Okay, so hopefully that all makes sense. And if that's okay, there is, sorry for all the scrolling, there is the practical 2, which I'll just invite everyone to have a go of now in their peer support groups. And we'll come back together at 12:25, just to wrap up. But just to remember, if anyone's having issues with forecast tools, the !pip space install space forecast -tools in a new cell in Jupyter Notebook, and that will download, and you should be able to get going. Again, any issues, please let me know. Okay, I shall open the breakout rooms. See you back at 12:25.
Elliot, hello?
Yep.
Hi. I had an issue before with the month, what do you call this? Is it days and months command? And I couldn't seem to get it to work.
Sure. Which was that, on the code along or on the first practical?
On the first practical.
Cool. Right. Let me just get my solutions up. Okay. Whereabouts was that? Sorry.
That is in step 6 of the first practical.
Oh, yeah. Let's have a look. Right. I'm just thinking, you're on code, aren't you?
Yeah, it seems like days and month didn't work, but then I tried it on my personal computer on Anaconda Jupyter Notebook,
Sure.
and it didn't work there either. So I'm just thinking, oh, what have I done wrong? I must have done something wrong.
Okay. Out of interest, when you try and just call the, I'm still sharing my screen, aren't I?
Yeah, yeah.
Yeah, cool. Oh, sorry. It would help if I.
Oh, it's reattends. I put in the whole data set. Maybe that was what's wrong.
Ah, okay.
Do that. Maybe that would work. Yes.
Not a problem. That was
What
an easy fix.
column? You have to specify what column.
Well, no, so reattends alone. Oh, sorry. Yes. So reattends, and then from that, we're pulling out the index. Oop, would help if I could tell the spell. And then the dot days in month. And you have to have made sure that you've set the frequency.
I had, but I know it's still not working.
So, I mean, literally, if you layer it on, if you start with the variable or the data frame name reattends.
My data frame isn't called reattends, it's just TS1.
Okay, but when you call TS1, does it look like a data frame?
Yes.
Yeah, and when you append that, so you TS1.index.
TS1.index.
Does it say date time index and then parentheses and then look like a list of dates?
I'm not too sure. It's actually very slow. Maybe I'll try in the other one. So it was. I have closed it now. Practical, yes, practical one. Okay. So if I, what you saying to do? Sorry,
So
TS1
ts1.index. Yeah.
Yeah, if I run this, yes, I have all the dates on it like that. Yeah.
And does it say at the end D-type datetime 64NS?
No, it says D-type object name date.
Okay, so I think maybe possibly a step's been missed out further up. So just to make sure that, I don't know if you can see my screen, but when you're importing TS1, when you're using the PD read CSV, you've got the index col. It sounds like that's correct, but then parse dates equals true.
I do not have that. I have index col equals date. So where do I have to put parse date equals
So
true?
after that, so after index col equals date, comma,
Okay.
and then parse dates, parse underscore dates equals true, comma,
True with a capital T.
yep,
Yeah.
Comma, day first, no underscore equals true with a capital T.
Okay, so it matters what order you put these things in.
No, they can go in any order.
Then I'll just leave it. And then if I run this.
And then you need, after you've run that, you've then got to set the frequency to month start. So it'd be ts1.index.freq equals ms.
Yeah.
But again, all the solutions are going to go online over lunchtime.
Thank you. So now then I should be able to use my, what do you call it? Days.
Oh, yeah. Days in month.
Days underscore.
In underscore month.
Okay, and this should work. Oh, yes, it's worked now. Okay.
Oh, excellent. Very good. Very good.
Okay, now I need to try this other one.
All right. Good luck.
Thank you.
Thanks. Hello again, everyone, and thanks for rejoining the main session. I just saw that someone in Apple Mac asked for some help. I don't know if it's a question they're brave enough to share with everyone. If not, feel free to hang on to the end of the call, but now's your opportunity. Okay. Well, rather than keep everyone hanging on, I'm just hope everyone was able to work their way through that all right. I'm just trying to get my screen share to work. Hopefully you can all see my and the only thing I want to draw everyone's attention to is just the errors again, just to look at which was better, the naive one or the seasonal naive. And just before I do, obviously just looking at the kind of the trend and the movements of the graph, it may have come as a bit of a surprise that the naive error gave a less, a smaller error. So when looking at the mean absolute error, these are actually in the same units as the rest of the data. Or if we're looking at as the percentage error, you can see it's less than a third. And it's all to do with when you've got the seasonal naive, you're moving up and down, what I mean? It does replicate the pattern. But if, you get kind of completely off in that step, then when the prediction's going one way and the actual data is going down, you kind of diverge even more, and so that's what can compound the errors. Where at least with the naive one, you're kind of staying static, and as we saw, that data had a kind of downward overall trend. So it is worthwhile always looking at these naive forecasts and just seeing how well each of those predicts, and to see whether or not there's going to be much more of a gain by going down the pain and effort of something a bit bigger. And even when you do use something like profit, always compare back. And then just so you can say, well, actually, yes, using profit was worth the time and effort because it offered an advantage X% better than the others. So hopefully that was a good introduction overall to time series and forecasting. And this afternoon, I'm excited to take you through profits. It's a really great package. It's incredibly easy to use. It's very, very easy. They've taken all the hard work out of it for you. And so hopefully you'll get a lot of value out of the session this afternoon. But other than that, I'll put the solutions onto GitHub right now, and I will see you all at 1:30 this afternoon. All right, have a nice lunch, everyone, and see you at 1:30. As always, I'll leave the window open.